Hello and welcome. My name is Vishwanath M. In this video, let us try to learn and understand a very beautiful concept called binary search trees. If you're following the VTU syllabus, this is program number 10 of Data Structures Laboratory. Let us have a brief introduction about the concept of binary search trees. Binary search trees is a very efficient data structure. Why I say that is because the operations related to data structures, that is insertion, searching, sorting, etc., is more efficient than other data structures. Let me give you a very simple example. So we have a binary search tree over here. So as you can see, there is some order that the binary search tree follows. Now the same elements can be inserted in an array. In an array, the elements are just a sequential collection of elements. I'll give you a very simple example using which you will understand the value of binary search trees. Now, in binary search tree, the core concept is that from any node, the left child or the left branch of the tree will always have elements smaller than the node itself, that is the node under consideration, and elements on the right or the branch to the right or the right child is always larger than the node itself. So this is the core concept of binary search trees, and the basics of trees we already know, or I assume that the reader should know, that the topmost or the first element in the tree is called the root node, and the last elements or the nodes which have no further children are called leaf nodes, and these are intermediate nodes you could consider. So in binary search trees, this is the concept one should remember, that from every node under consideration, the branch of the tree to the left is always containing smaller elements, and to the right it is always containing larger elements. So as you could see, when considering 40, all the elements to the left are smaller, all the elements to the right are larger than 40 itself, and the same applies it at each level of the tree. So at 30, or at this level, all the elements to the left are smaller than 30 and all the elements to the right are greater than 30, and the same goes with this node as well. So having this understanding in the background, now let us consider a very simple example of, let's say, searching. If we had so this binary search tree contains 7 nodes or 7 elements. 7 elements could also be represented in an array. So let's just imagine there was an array like this and all the elements were written sequentially. And suppose you wanted to search the last element of the array, and if you're following something like a linear search, we will have to find out all the you will have to traverse through all the elements of the array and then reach the last node, and then there you will find the node which is required or the element which is required. Whereas in the binary search tree, since there is some order, since we know that elements on the left are always smaller and elements on the right are always larger, we could cut down the number of operations by almost half, and hence improving efficiency. So this was a very vague example or a simple example to understand the value of binary search tree. So after having understood the concept of binary search tree, let us dive into the program, also learning some background or some related concept. As we understand each function in the program, we also appreciate the value or the concept behind each of them. So this was the introduction. So let us now dive into the program. Like any other C program, we have a set of header files, stdio and stdlib.h. stdlib.h is included in the program because we are using dynamic memory allocation functions. So hence we have to include the library stdlib.h. stdio we already know, it is used for input-output operations. A good understanding of struct or structures is required in order to understand the program. So let me give a very brief of the concept of struct or structures. So struct is a keyword which is used to create structures. So what is a structure? Structure is as simple as a user defined data type. How we also have data types like int, char, void, double, etc. They are all predefined data types if we want to create a data type of our own, we can create that using structures, and hence it is also called as user defined data type. So or structure allows us to combine data types or elements of different types or of the same type and consider the whole thing as one entity. So in this case, this structure or this structure called BST, you would be guessing that BST means binary search tree, that is right. So structure BST contains 3 elements. The first element is data of the type integer. The second and third elements are basically pointers. So what you have to understand at the background is, though it looks a little long and complex, it is at the core or at the heart, it is just a pointer. So just like how we create int star a or int star b, where a and b are pointers of type integer, here L child and R child are pointers of type struct BST. So struct BST is the name of the data type. So just imagine int is replaced by struct BST, and star means that we are creating L child as a pointer, and the same goes with R child. Always remember, when we create the user defined data type or when we define a structure, we always have to use semicolon. So that is a mandatory requirement, else you would see some error. So we have understood what a structure means. So this is not how it would be internally, but for our understanding, this is a good way to understand the value of structure. So consider this as one node, or this as one element of type struct BST. Always you must say struct BST, meaning it is a structure and its name is BST. So BST has 3 elements, and we have represented it like this for our understanding. So this will be an integer, and it is called data, and we have 2 pointers, pointer to the left child and pointer to the right child. So this is all we need in order to create something like a binary search tree, because at every node these understand or like have an understanding like these pointers or these arrows are pointers, and when I say pointer, they are addresses. So 40 will have to have an address to the location of where 30 is stored, and it will also have to have the address of the location where 50 is stored. The same goes with 30 and the same goes with 35. So this is each node will have 2 pointers or 2 addresses, pointer to the left and pointer to the right, and 40 need not have all the pointers in its left tree, because the subsequent node, that is 30, will have the addresses of its children, and the same goes on the right branch as well. So this is how we create a structure called BST, and we are defining what BST contains. Now coming back to the program, as I said earlier, that struct BST would kind of be longer and make sound complex to pronounce. So what we do using this facility in C, we use this thing called type def, or basically what we are doing is we are defining. So we are defining the data type struct BST, which is a struct BST as a pointer, and we are instead of referring it to as struct BST star, we can just refer it to as node. So just like how you could just have a nickname to your friend who has a very long name, this is exactly the same. So type def is basically creating a nickname or creating a type or defining a type, you could say. So instead of using struct BST star, you could just use node, and node literally means struct BST star. So I hope I have made it clear. So node literally is a nickname of struct BST star. So always remember, node is a pointer type data type. So wherever you see node, it is a pointer type data type. Have that in mind as a background. So we have created the structure. So basically in this program, we will have to create a node, that is create each independent entity. We will have to insert them into the tree. So initially we just create independent entities like this and insert the value, and it would form a tree only if it is appropriately linked or it is appropriately inserted into the binary tree. So we need a function called insert. So let us understand what create and insert means at a logical level. So as I already said, create function creates a node which is independent. It is not linked to any node, and initially the pointers will be just null, that is, it is not pointing to any address. And then insert function, what it does, it considers the node that is created, it takes the node that is created and it connects to the tree, it connects or it inserts at the appropriate position. So what would be null initially would then have the address of the relevant children or relevant nodes. So we know what create and insert does in the function. Search function, or as you would guess, is used to search whether a node is present in the tree. For example, this is, remember, search function just indicates whether a value is present or not, it does not indicate the position or anything like that. So void search basically returns if the element is present or not present. So that was search function. A very important concept in binary search tree is traversal. So there are three types of traversal. So traversal literally means how you could process or how you could read a binary search tree. That is the literal meaning of traversal. And there are three defined ways, that is Inorder, Preorder and Postorder. We will I know we will have to write the code to the function, or you have to implement the traversal, but it is essential to have a understanding of the concept before we write the program. So at the heart, preorder literally means pre-order, that is order. See, you could think of it like this: order literally means left to right, so left and right indicates order. Pre, in and post indicates the position of the central node. So this is a this is how it is very interesting. Order, you could take it as left and right. So let's have a very simple binary search tree: 1 2 3. Pre-order, pre indicates that C or the central node comes pre or before. So when we are reading this tree in a pre-order traversal, we will first read the central node, that is 2, and then left and right, that is 1 and 3. CLR. Moving on, in order. In order means it is in order as it sounds. So the central node is in order. Always remember, it is always left and right, it is never right to left in any of these traversals. So left and right is already there, but we are reading, or we are traversing the central node in order. That is, we read the left node first, then the central node, then the right node. So hence the name in order. So it would be 1 2 and 3. Post order. So again, order, I said order always means left and right, but we have post here. Post indicates that after reading the left and right, we read the central node, so LRC. So what I would recommend is have a good understanding of what pre-order, in order and post order means, and then jump into the program, because having this understanding will make writing the program really a piece of cake. So in post order, it is left, right and center, hence it is 1 3 and 2. So this is a very simple example of pre-order, in order, post order traversal. So in the example, or in the execution, we will create this binary search tree, and we will see how the pre-order, in order, post order implements, and we will understand how this tree is read in different orders, or how it is traversed in different orders. So that was about the three functions, and we know that we will have to create a menu driven function and a menu driven program, and that is done in the main function. So that is what is there in the main function. So we have an overview of the program. So now let us very quickly understand each function and then jump on to the execution. We already know what struct BST and typedef struct BST star node means. So always remember, node is a nickname for struct BST star, and node is a pointer type data type. So these are things you could use it in your Viva as well while explaining the program. Node create. So we are creating a function just like any other function. We will want a data type. So here node is a data type, but remember, it is a data type of a pointer. So node is struct BST star. Node create. Create is the function name, and as I already said, it just creates a node or creates an entity. Inside node create function, we create a temporary pointer called temp, or create a temporary node called temp, and as I said, in the function we are using dynamic memory allocation functions. So this is the function which will allocate the memory of a known size. So we know what is the size of this binary search tree node, so we just call the function size of struct BST. So in other programs you might probably encounter malloc size of int. So always remember, struct BST is as good as any other data type, but this is a data type that we have created. So and always malloc function returns a pointer, so and it returns a void type pointer, but we know that in the program we need this type called node, so we are typecasting it. So we are if we insert node in parenthesis, basically that will convert the return type of malloc from void star to node star, or node, because node by itself is by default is a pointer. So I hope I've made it clear. Temp is now having the address to the temporarily created space. So this is it is nothing but a space or a memory allocated in the let us understand, a chunk of memory allocated in memory. Alright, so after we have created the space, or after we have the memory, we just want the value, because that's the only thing we will need to insert into the node or the entity. So printf enter the value, and we accept the value using scanf. So these are things which you will understand if you have understood pointers really well. So we know that temp is a pointer. So while accessing that pointer, this arrow mark is what we use. So ampersand temp is the address of the pointer. So basically whatever the value that we have entered, we are inserting that into the address of temp. So that is address of temp, that too in particular address where data has to be stored. So that is the understanding of this scanf function. Ampersand temp means the address of data. So since temp is a pointer to the whole entity, we have to specifically point to the data element or data entity. So ampersand temp of data is where the value gets stored. And initially, as I said, it is an independent entity. It is not linked to any node. Hence, we want the L child and R child pointers initially to be null. And once it is created, that is, if data is entered and the left and right pointers are made as null, we can just return the temp. That is, we can return the address, or we can return the pointer. So we have understood node create function. So you would probably appreciate how the concept that we understood is making complete sense while we are understanding the program. Next, let us jump to insert function. So we already have the node created. So in insert function, always remember that we will have two parameters in the function prototype. That is, so while we are inserting a node, or we need the root node, because we always start from the root node and go left or right based on whether it is smaller or larger. So we always want the root node, and we want the new node, that is the node that has to be inserted. So if we just had 40, so if we had to insert 30, we need 40 first of all, that is the root node, and we will also need the new node, that is 30. So that is the logic behind why we need two parameters, node root and node new node. So we know the concept, that is, if it is smaller, it goes to the left, if it is larger, it goes to the right. So the same is implemented in the code here. If new node of data, so always again going back to the concept of pointers, new node represents the whole entity, or assume that new node represents this complete box which has 3 compartments, and data is one of the component of the box. So how do you access the particular component? By using the arrow mark, new node arrow mark data. So if new node of data is smaller than root of data, root is this root node. So if new node of data is smaller than root node of data, we know that it has to go to the left. Hence, if root of L child is null, that is, if again initially the root node will always if there are no more elements in the tree, the root node will just be the node itself, and it will the left and right pointers will have null. If that is the case, if root of L child is equals to null, then whatever the node that we have that is asked to insert that as the left child of root. So read the code like this: if the if the left child of root, if it is a null pointer, or if the left child is none, or it is just having a null pointer, then insert the new node as the left child of root. So that is the understanding. But if that is not the case, that is, if let's say the root already has left and right children, but the the intermediate nodes have to be used as the parent now. What I'm trying to say is, so we already have 40 and 30 and 50. Let's suppose if 25 has to be inserted, 25 cannot be inserted to the left child of 40, but 25 has to be inserted to the left child of 30. That is to the left child of 30 is where 25 will get inserted. So that happens here. So by now we would have understood that if root is empty, we can directly insert to the left and right child. But if root is not empty, that is, if root already has some children, so it has to go down the tree. So whatever the new node has to be inserted, it has to go down the family tree, or let us call it the binary search tree. So let's for easier understanding, suppose there is a new entity that has to be inserted to the tree. So this is the root. Root has a child has a child again. So suppose a new element had to be inserted, it will be the child of the last or the leaf node. So that how do we do certain things repetitively? There is the clue. So there are two ways. One is doing it iteratively. Other method is doing it recursively. Here it is just recursive, because we see the root node, we see if it is if it doesn't have any children. If it doesn't have any children, we will insert it to the root node itself. If not, we will check the subsequent nodes. So we are doing a recursive task. Hence you would see that insert function is calling itself. So it is a recursive function. So else, if we understood the if part, else insert root of L child comma new node. That is, what does root of L child mean? Root of L child means 30. So we will call the insert function by passing root of L child. So in the next iteration, or whenever in the next not iteration, in the next recursive call, insert node will have this root of left child. That is, it will have 30 as the node, and whatever was the new node will simply be there. So it will run the function recursively until it goes to the leaf node and then inserts it appropriately. So I hope we have understood the left insertion correctly. That is, it is very simple. So this is the concept you have to remember. If the new node of data is smaller than root of data, then it will go to the left subtree or left children. So that is why you would see all the pointers are left or L child, and it is the reverse here. If the new node of data is greater, or greater means larger than the root node, we go down the right sub branch of the tree. So if root of R child is null, that is, again, if the root node has no children initially, we can insert the new node as the child of right child of root node. Else we will just call the insert function recursively, but we will go down the right sub branch of the tree. I hope we have understood insert function now. All right. Now we are left with search function. As I said, search function basically indicates the presence, if it is present or not. It does not indicate any position or anything like that. How do we identify if an element is present in the tree? So we first need what is the element to be searched. So we create an element called key, node cur or current, you could call it. So it is again a pointer of type node cur. So if root is equals to null, that means if the root node itself is null, basically it means BST is empty. That is, we have not created the binary search tree itself, so we can just return. But that won't be the case normally if you have executed the program correctly. Printer, enter element to be inserted, and we accept the element, that is key. So we start. So basically, you could read this cur or current node has a temporary location or a temporary pointer. So we start from the root. So cur is initialized to root, and while cur is not equals to null. So this is very interesting. So binary search tree is a beautiful concept because you could literally understand looking at the image. So we start from the root node. So the cur will initially have or point at root. what does while function do? While function repeats the set of statements until the condition fails, until as long as the condition is true. So cur is not equals to null. That is, basically what it does is, starting from the root node, it will go either left or right. That condition happens here. But what does the condition mean? As long as or until the current is not null. That is, all the leaf once it has reached the leaf nodes, the suppose it goes further down the tree, there is no node there, or there is no element there, and hence the curve will be pointing to null. That is when we can conclude that once we have seen the whole tree, or once we have seen the appropriate part of the tree, we can infer that it is not present. So that is the condition in the while loop. While current is not equals to null, so as long as, or you could read that, yeah, as long as current is not equals to null, execute the set of statements. What is a set of statements? If cur of data, again this is going back to the concept of pointers. If so, assume that current is this box and data is the component. Current of data, that is data component in cur, if it is equals to key, we can print key element is present in the BST. It is just a yes or no question, it is present, and we return. If key is smaller, so again in the beginning of the video I've explained that one of the advantage of this binary search tree is we can improve the efficiency of searching. So if key is smaller than the current of data, so assume that the current is initially here, that is the root node. If the key, or whatever is the key, let's assume that key was 35. So since key 35 is smaller than 40, what we do is we move along the left child, or along the left sub branch of the tree. Current is equals to current of L child. So we are not really bothering about the right part. So that is the efficiency part of binary search tree. The other way around, if the key is not smaller than cur of data, so let's assume that the key was, let's say, 45, then it will search on the right tree. So current is equals to current of right child. So here it is a what while loop is doing is, it is doing it iteratively. So it is, as long as the condition is true, it will repeat the set of statements iteratively. And if the while loop has executed completely, that is what that means is, once while loop has seen this condition, if current is, when the current becomes null, that is it comes out of the tree, we know that the element is not present. So we just print the message, key element is not found in the BST. So we have understood the search function. Next, we are left with Inorder, Preorder, and Postorder. Understanding this is a piece of cake if you have understood what I explained here. That is the center left right convention. So let us just translate this logic into code here. Void Inorder node of root. So always to traverse the tree, we just need the root. We don't need anything else. So once we have access to the root, we can just go left, right, or on whatever the order is based on the function name. So void Inorder node root. So understand, look at all the three functions together. So all the three look very similar. They look identical. The difference only comes where we are printing the center node. So look at both of these parallelly, so that it becomes easier to understand. So I'm just zooming it for better understanding. Void Inorder. So in order, what we know is, we first see the left node, then we print, then we see the center node, then we see the right node. If root is not equals to null, so this is a condition we have to check in all the three functions. That is, when will root be null? When we have not created the binary search tree itself. So if root is not equals to null, in order of root of L child. So again, this is a recursive function, because in order function is calling itself. In order of root of left child. Root of left child. So we go down the tree on the left side first, then we print the data of the current node. So that is the central node. So what is happening here? Printf percentage the root of data. Data is the component where the value is present. So now we went down the left tree. So assuming we were here, we went down here, that is along the left direction. Then we printed the value 2, and then we come down the right direction. So this is what happens in order. So if you have understood this, understanding pre-order and post-order will take no time. In pre-order, we know that we print the central node first. So hence the print statement comes first, printf %d root of data, and then we pre-order, that is we continue the traversal further along the direction we know, that is first we print the central node, then we go down the left, and then we go down the right. Next, post order. We know that in the post order we first go along the left and right subtrees and then print the central node. So hence you would see that post order is going down the left child and then it goes down the right child, then it prints the central node. So I hope this concept or this understanding of the concept made this writing the code for in-order, pre-order and post-order traversal lot more easier and lot more meaningful. So we are now only left with the main function. In the main function, basically we are just creating the major part is we are creating a menu driven program. So we create some integer type values, that is ch denotes the choice because it's a menu driven program and it has to have choice, and key here, what does key indicate? Key here indicates the key here indicates well, probably even key is not even required here. Anyway, let's go down the program first and then understand the importance of the integer type values or integer type variables here. So again, going back to the concept of node. So node is just a nickname of struct BST star, that is pointer of type struct BST. Node root, initially it will be null obviously because initially we are creating a root node which is just empty, and then we create a new node because every time we create a new entity or new node, we will have to first create a new node and then we first have to create it, then we have to insert it. So while one is an infinite while loop, it keeps on execution. So that means that one of the choices will have the exit statement. So the first line is just printing BST menu, that is just to make things more user friendly. So we create the message, we display this message called BST menu, and then create a binary search tree. Then choice number 2 will search, choice number 3 will be for the binary search tree traversals, that is all the 3 traversals, and choice number 4 will be for exit. After we have printed the menu, we will ask for choice, printf enter your choice, scanf %d and ch. So ch is being used here. So we already know that for any menu driven program they are using this switch facility or switch construct. So switch of choice, if case is 1, if ch is 1, that is it means that we are creating a binary search tree. So the first question is how many elements in the binary search tree. So we input that value here, enter the number of elements. So scanf %d and n. So we know that n is being used here. N indicates number of elements. Now we know what is I also. I is used in the for loop. It is for iterary purposes. For I is equals to 1, I smaller than equals to n, I plus plus, a new node. So basically for when we are creating a binary search tree, we first have to create the nodes. We have already seen understood this. We first have to create the nodes. So we are creating the new node first. So we call the create function, and if root is equals to null, that is we know that initially we have initialized root to null, that is before starting anything, before creating the tree, root will be null. So this condition this condition will satisfy in the first time. So if root is equals to null, so whatever was the new node that we created, so initially new node will be when we create 40. So 40 will then be the root node. So new node will be the root node. Remember, this happens only the first time. Else what we have to do is we just call the insert function, because after it is created we just want it to be inserted appropriately. For the root node there is no insertion because root node is the first element in the binary search tree. So we just initialize what is the root node. So that is it about the creation of binary search tree. Once the for loop is executed, we break out of the for loop. So we break out of the first case. So after the first case is done, let us understand the second case. In second case, that is search, we simply call the function search, and while calling we know that the search function just requires the root, that nothing else. So we are passing the value root here, search of root, and we break. Case 3, if root is equals to null, if root is equals to null, that is what is the case 3? It is binary search traversal. So if root is equals to null, that means the tree is not even created, and this doesn't happen if you have correctly executing the program. So but it is just a check we need to make. Else printf, we just traverse the binary search tree in all the tree traversal methods: preorder, inorder, postorder, preorder, inorder, postorder. So we just print a message preorder display and call the function, and we call the respective function inorder and postorder for each message. And again case 3 will break after the preorder, inorder, postorder traversal of the tree is done. And the last case, that is case 4, is exit. So exit is a system function. So we just call exit function and it will just come out of the execution. So what we have understood now, or what we just discovered, is we don't even need these two variables. So we can just remove it for space and simplicity constraints. So we are just using 3 integer type variables, that is choice, I for the for loop, n for the number of elements. So we have understood the whole program at the moment. So we have understood all the functions, we have understood the concepts. So what we now have to do is execute the program keeping this image parallelly. So let us do that now. We know how to execute a C program. Using the GCC compiler, GCC, and the program name is P10 dot C. So if it comes to the next line and if the cursor is blinking, that means there are no errors in the program. If there are no errors, we know how to execute the program, that is /a .out. This is the way to execute a C program. There we go. So it is now, we know that all C programs start execution from the main. So main function has started execution. We have printed these 3 messages. We are waiting for the choice. So let us now very quickly do the execution because we have everything on the image here. So enter your choice. We first have to create the binary search tree. So my choice will be 1. Enter the number of elements. So it is 1, 2, 3, 4, 5, 6, 7. So it is a total of 7 elements. So I enter 7. Enter the value. Now again, for execution, it is very important. Please pay attention here. While you enter the values, the practice to be followed is enter the elements in the first level or in the root level, then enter the elements in the subsequent levels from left to right. So what I am trying to say is, first you enter 40, that is the root node, no confusion there, and then the next element would be 30, then 50. So you are just reading it. This is the normal way we read any normal way we have been reading books and pages. So we read from left to right and top to bottom. So left to right, so it was 40, so we entered 40. Left to right, we have come down top to bottom, 30 and 50. So we enter 30 now. Next iteration, next element we enter 50, that is left to right, top to bottom. 30 and 50 is entered. Next we come down, that is we are coming top to bottom and we are going left to right. So now we are come to the last level. So the last level of elements will have 25, 35, 45 and 55. It is very important for the users to enter the elements in the practice that we just understood, that is top to bottom, left to right, 40, 30, 50 and all the elements on the last node, on the last level. So we have entered 7 elements. Just click enter. That means the binary search tree is now inserted, or a binary search tree is now created. Okay. Now before we try searching, let us see the traversal first. So we'll let our next choice be 3. So that means binary search tree will be traversed in the 3 methods that we know, that is preorder, inorder and postorder. There we go. Preorder, inorder and postorder display. So let us see if it is doing it correctly or if it is following the same convention. Preorder. So what does preorder means? Center, left and right. So we start from here. Center is 40, so we have printed 40, left and right. So what is the center is 40, and then we go down the left. So this is where it is one has to pay attention. If it is just a one level tree, if there is only two children for the root node, then it is as simple as center, left and right. But since this has multiple levels, after the center is printed or after the center is processed, we enter the left tree, or we enter the left part of the binary search tree. So basically we are again at the center. What that means is, once we have entered 40, we have come down the left tree. That means we again have a center. So the same convention follows again. That is, we print this center first. So hence we are printing the center first, and then we go down. And then here, since it has no children, so we will just print the left and right, 30, 20 and 35. So we printed the center first. We went down the left tree. In the left tree again we followed the same convention, that is center, left and right. So we have understood till 35, 40, 30, 25 and 35. Now what we have done is, we have completed the center, we have completed the left part, center, and completed the whole left part. Then we are coming to the right part. So what you have to see, how the best way to guess, or like best way to write the program, or write the output is, consider each of these as individual trees. So we see that 40 has two children, but each children has its own trees. So always go until you reach the leaf nodes, write the output, and then come back to the top of the tree and go the other branch. So let us now understand in order. In order, we know that we first go the left path, that is, we enter the tree and go deep down the left subtrees. So we have entered 40, but we have entered the tree and we go down left. This is again center, but the order the rule in order means says that we first go down the left. So we go down the left, so that is, we first print 25, and after the leftmost, or the leaf of the left tree is printed, we print the center, that is, immediate parent is 30, then immediate right, so 25, 30 and 35. So have this simple tree as understanding, and then correlate to bigger trees, or correlate to binary search trees which have multiple levels. So left, center and right. So go deep down, left, center and right, 25, 30, 35, 25, 30, 35. So we have completed one level. So we have completed the left part. So going back again, so 40 now has consider this whole thing as a left child of 40. So the left child is completed. So L part is completed. Now we can print 40. So after this is printed, we are printing 40. So we are printing 40, and then we go down the right. So I hope I'm making it understandable by repeating it multiple times. At each level, 40 consider the whole as its child, then go even more granular, that is, consider 30 and see its children. If 25 children, go and finish its children first, and then go up the tree. So that is the convention to be followed. Let us now understand the post order. In post order, we know that it is left, right and center. So 40 has left and right children. So this is the left child, and this is the right child, or the left subtree, right subtree. Finish the left subtree first, that is, enter the left subtree, 30. Again follow the same convention, left, right and center. For this tree, left, right and center, 25, 35, 30. So we have completed the left child, or the left subtree of 40. Then the rule says, in post order, we next have to consider the right subtree. So the right subtree is here. In right subtree again, what we have to follow is left, right and center. In this tree, left, right and center, 45, 55 and 50, 45, 55, 50. So at the higher level, at the root node level, we have completed the left tree. We have completed the left tree. We have completed the right tree. R is completed. Now we are only left with C, that is central node, or the root node, which is 40 here. Another interesting fact one could know, or one could note down somewhere is, in preorder, the root node will always be printed first. In preorder, the root of the tree will be printed first. In inorder, it will be somewhere in the middle. In post order, it will always be at the right end, or the last element to be printed. So we have understood preorder, inorder, postorder. I recommend the readers to understand the concept, try out and write on paper multiple trees and write the preorder, inorder and postorder, because it also helps in your theory exams, and then understand the execution parallelly. So we have understood binary search tree traversal now. Let us now quickly try search, because it is very simple. Enter the element to be searched. So let us enter, let's say 50. So it says key element is present in the BST. Let us try search again, and let us enter element like 100, which is not there. So as expected, it says key element is not found in the BST. So we have understood all the three menu options or menu entries. So the last option or exit option just basically exits the execution of the program. So we have created a binary search tree referring to a tree here, and then we have completed the traversals. We have understood how to write the traversals. So again and again, please have this concept in mind, the CLR, LCR and LRC convention in mind, and try to write the programs and write the solve binary searches on paper, and then solve the programs. I hope I have made the concept of binary search trees understandable and easy to write and execute. That was all in this video. Thank you.